Hello, this podcast is on describing motion visually. We're going to learn how to create and interpret motion maps. Motion maps are simply a way to visualize an object's motion. Let's take a look at several different types of motion and see if you can figure out what the dots represent. Do you have it figured out? Well, the dots represent an object's position at a specific point in time. One dot is equal to 1 second of clock time beginning at t equals 0 seconds. Now you can have your dots represent more than 1 second, but if you're doing that, you want to indicate that on your diagram. So if there's no indication, 1 dot equals 1 second. 2 dots equals 1 second of elapsed time. In other words, from here to here is 1 second. 3 dots represents 2 seconds of elapsed time, and so on. When you're doing a motion diagram, if you're doing it for 10 seconds, you're going to have 11 dots. The space between the 2 dots is equal to the change in position. Notice here, there's not much change in position in 1 second, but now here there's quite a bit of change in position in 1 second. Let's learn how to create a motion map. First, we need some position time data. So here's a table with our time and position data for an object in motion. Next, let's bring over our rules from the previous slide, and notice we've added a fourth rule dealing with the velocity vector, and we're going to use arrows to represent the velocity vector. Arrows are an awesome way to visually represent vectors, because vectors have both magnitude and direction, and arrows have both magnitude and direction also. The length of the arrow is equal to the magnitude of the vector quantity, and the direction the arrow is pointing, or its tip, is equal to the direction of the vector quantity. Next, we have to put in our position line, and we'll label it X for position, M for the units meters, and we put in a grid, and now let's number our grid. Remember, these are positions in meters, and here is the origin. Now we're ready to plot our points. At time 0, the object is at 1 meter. So my first dot's going to go at 1 meter. Notice a second later, at 1 second, it's still at 1 meter. So I'm going to stack the dot. When something's not moving, we stack the dots. At time equals 2 seconds, it's also at 1 meter. But notice at 2 seconds, it starts moving because at 3 seconds, it's at 3 meters. So we're going to add our velocity arrow pointing to the right, showing that the object's moving to the right. And we're going to put in our next dot at 3 meters. Now, when it comes to drawing the length of the arrow, what you typically do is you draw the arrow halfway to the next dot. So notice the distance between the dots, and I drew the arrow half that distance. As long as you're spacing your dots correctly, if you draw your arrows halfway to the next dot, you're always going to have them the right length for the amount of velocity. Okay, and we'll go on with our next second, which is the 4th second, and that's at position 5. And then at 5 seconds, we're at position 7. But notice here, at 5 seconds, it changes direction, and the object starts to head leftward. So the way we handle that is we put the dot at 7 meters, because that's where it's at 5 seconds, but we draw the arrow pointing to the left. And I went ahead and put the dot up here because we're going to have to start to backtrack, and we don't want to backtrack over our existing arrows and dots. What's important here is we only have 1 dot. You can't put a dot down here and a dot up here, because if you do that, that's meaning that the object stood still for a second, and we can see by looking at the data it did not stand still. It changed directions immediately. Now we'll continue on with our leftward motion, and notice the arrows are smaller, and that's because when it moves leftward, it's only changing position by 1 meter every second. So my arrow once again is only going to go halfway to the next dot, but because it's not moving as fast, the dots are spaced closer together, and therefore my arrow is only half the length as my original rightward arrows. And so we'll go ahead and finish this up, and when we get to 8 seconds, the object is at position 4. So this represents the motion, and let's just review some key points about this. The first dot is always 0 seconds. Here's an easy way to remember that. If you have a stopwatch on your cell phone, when you turn it on, it starts at 0 seconds. When an object's at rest, we stack the dots vertically. When we change direction, we only have one dot. We don't have two here. Now you could put the dot here and then just have this leftward arrow without a dot up here. I choose to do it this way, but either way is correct. But what you cannot do is have a dot here and a dot here, because if you stack dots, it means it stood still. We notice that when the object's moving faster, which in its rightward direction, it's moving faster than in its leftward direction. So we notice that the dot spacing is wider and the arrows are longer. And conversely, when the object's moving slower, the dots are spaced closer together because the object's not changing position as much in 1 second. And of course, the arrows are shorter. And finally, on the last dot, the arrow is optional. I like to include it, but you don't have to. And the reason for that is we don't really know where it is at 9 seconds. So we don't know that it's only moving 1 meter every second leftward. So you can either continue with the same type of arrow that you had in the previous second, or you can leave this arrow off. Your choice. Let's go and look at how we interpret position time maps, and this is pretty much just the reverse process of what we do for creating it. We need to remember our rules, so I have them listed down here, and we look at our motion map and we look at our line. Now a couple things I want to point out: the origin here is not all the way at the left, and we have some negative positions, and that's okay. Your origin doesn't always have to be at the left hand side of your number line, and in this case the object started here at position 3. So we're just going to go dot by dot and fill in the time and position data. So remember, the first dot is always time equals 0. So we're going to go ahead and put in 0, and it's at position 3. So we go ahead and put in position 3. We go on to our next dot, which is going to be 1 second, and it's at position 1. Our third dot is going to be 2 seconds, and it's at position -1. Our fourth dot is going to be 3 seconds, and it's at position -2. And now when we get to our fifth dot, we're going to change direction. And we only have one dot when we change directions. At second 4, the position is -3. At 5 seconds, it's at -1. And at 6 seconds, it's at 1 in the positive direction. And notice at 7 seconds, because the dots are stacked, at 7 seconds it's going to be at the same position, and then it starts moving again. So at 8 seconds we're at position 3. So this is how you interpret a motion map and get position time data from it. Well, this wraps up what we wanted to learn about visually representing motion. So let's go ahead and review what we learned about motion maps. We have a position line which measures the location. Dots show the object's position every second. The first dot is always going to be time equals 0 seconds. 2 dots means we have an elapsed time of 1 second. 3 dots, an elapsed time of 2 seconds, and so on. You're always going to have one more dot than you have total elapsed time. Dot spacing increases as speed increases because the object is changing its position more in that second. And we use arrows to represent the object's velocity. The length of the arrow represents the magnitude, longer arrows, faster speed, and the tip or the direction of the arrow equals the direction of the velocity. Well, this wraps up our podcast. I hope it helped you understand how to visually represent motion, and have a good day.